Hello, welcome to part 2 about quadrilaterals. And I wanted to start off with something I should have mentioned in the first video. These 3 videos on quadrilaterals do not have any actual proofs in them. All of the properties that I'm going through would require their own proofs. Those I'll be doing in class. Let's revisit our Venn diagram, which represents the different types of quadrilaterals. And let's take a look at a couple more conditional statements. So let's determine the truth value of this statement. If a shape is a trapezoid, then it is a kite. Well, if I'm going from one subset to another and they have no intersection at all, then this implies that a trapezoid cannot be a kite and vice versa. So this is never true, making it false. And how about this one? If a shape is a rhombus, then it is a rectangle. Well, this is an interesting situation because we do have an overlap, which would be the square is both a rhombus and a rectangle. But because one of these subsets is not completely inside the other, and all we have is an intersection, then the answer to this would be sometimes true. And anything that is sometimes true has a truth value of false. Alright, again in this video we'll be looking at trapezoids and isosceles trapezoids. And in part 3 we will take a look at parallelograms and the other special kinds of parallelograms, the rectangle, rhombus, and square. Back to trapezoid. Our definition of a trapezoid is a quadrilateral with exactly one pair of parallel sides. There are the parallel sides. Now for trapezoids we will be using some specific vocabulary. There are 2 bases. And the notation you'll often see is B1, B2. It just means base number 1 or base number 2. And these are interchangeable. The other 2 sides we will call legs. As for the angles of a trapezoid, the only one property that we will consistently have for every trapezoid involves the consecutive angles C and D, or B and A. But this property of them being supplementary does not apply to the base angles. So C and B do not follow this property. I would say the consecutive angles on the same leg. So B and A are on the same leg, therefore their sum is 180 degrees. They're supplementary. And angle C plus angle D also adds to 180. If you can recall our theorems involving parallel lines, pretend those are parallel, and a transversal, this is the same exact situation as our same side interior angles. The sum of these two is always 180, or these 2 same side interior angles are supplementary if the given lines are parallel. We will come across other formulas like perimeter, area, and then even more specifically an extra construction called a mid-segment, but we will not get into those in this video. Instead, let's look at the special case of trapezoid, and if we went back to the Venn diagram, what we're now doing is making a subset of trapezoids which are called isosceles, which I don't have enough room, so I'll just abbreviate isosceles trapezoids. A little coffee break. Good stuff. And here we have our page for isosceles trapezoid. We will combine the definition of trapezoid. So we're adding to the original definition of a trapezoid. Trapezoid has exactly one pair of parallel sides. These are the bases. An isosceles trapezoid has congruent legs. One of the properties of an isosceles trapezoid is not only are the consecutive angles on the same leg supplementary, as we saw in the previous slide, but now the base angles, meaning the 2 consecutive angles along the same base, angle B and angle A are congruent, as well as angle C and angle D. Another property of the isosceles trapezoid involves its diagonals. Its diagonals are always congruent. And this property maintains itself no matter what kind of isosceles trapezoid we create. before we leave the slide of isosceles trapezoids, think about whether or not we could prove these two highlighted triangles as congruent, and as a result, which corresponding parts could we also prove to be congruent. Our next video we will examine parallelograms.